This is Chapter 19, review for the AP exam. I'm going to go through number 14, which is a free response question, and number 15 as well. So turn to page, I guess it is 3 or 4 on the packet. So we have an equation here, hydrogen gas burning, according to this equation. Remember, this chapter is about delta H, delta S, delta G, thermodynamics. So we're going to deal with some heats. They want us to calculate the standard enthalpy change, a fancy word for heat, for the reaction represented above. Now they tell us that the molar enthalpy of formation, remember these are the numbers in the back of the book, the formations, each compound has a formation, heat of formation, how much heat it takes to form it. They tell that to us for water, which is negative 285.8. Now in order to get the delta H for a reaction, you can do products minus reactants. Remember, the heats of formations of the products minus the heats of formations of the reactants. And so, now in our case, the products is given to us, water. Oxygen and hydrogen are not given to us. And these also will not be given to you. There's no table that gives these to you on the AP exam. They want you to recognize that these are zeros. Anything in their elemental state has a delta H of 0. It also has a delta G of 0. Delta S's, however, actually S's, are not 0 because everything has an entropy, if you recall. So we do products minus reactants. Don't forget that we have 2 products, so we have to multiply this number by 2. So we get 2 times negative 285.8 minus, and then we'll have to add 2 times hydrogen, which is 0, plus 1 times oxygen, which is 0 as well. So effectively, we're just doubling this number, which gives us 571.6, negative 571.6 kilojoules per mole. Not too bad. So this would be the delta H that goes in the back of the equation now. Negative 571.6 kilojoules per mole. Good? Now B says, calculate the amount of heat in kilojoules that is released when 10 grams of H2 is burnt. Well, since we now have the relationship between H2, the moles of H2, and the heat, we can readily do this. A little stoichiometry, 10 grams of hydrogen, grams of hydrogen at the bottom, a mole of hydrogen on top. Hydrogen still weighs 2.02. Then we'll go from a mole of, or from moles of hydrogen into our kilojoules. We have that relationship. It is here. Notice that 2 moles of hydrogen require or give us negative 571.6 kilojoules. So it's important to put a 2 down here. You always relate the delta H that you figured out to the balanced equation. So that should give us a number that is roughly 1410 for significant figures, adjusted for significant figures. Notice I don't put the negative here because we're saying how much heat is released. We're already accounting for the release. So 1410 kilojoules. Part C says, given that the molar enthalpy of vaporization for H2O is 44 kilojoules per mole, what's the standard enthalpy change for this reaction? Now this reaction is actually very similar to the reaction above. The only difference is that our water is now a gas. This will require the use of Hess's law. And then remember Hess's law, I think it's like this, Hess's law, no, it's like this. Hess's law allows us to combine equations and cancel them out, and so arrive at a final equation. So the equation that we want to arrive at is this equation. The equation we're beginning with is this one, and the heat of vaporization for water. Now heat of vaporization for water is actually simply H2O liquid to H2O gas. It's how much heat it takes to vaporize water. This is given to us as delta H is 44.0. Right, so let's take this equation right down, and we got ourselves 2H2 plus O2 giving us H2O. Now this would be a liquid. I should stress these are gases, but this is a liquid, notice. So what we need to do is combine these 2 equations to give us this third equation. So we have to end up with 2 H2O gas on the right. Here is our H2O gas. We need 2 of them. Whoop, I'm sorry, I forgot a 2 right down here. For the liquid, notice 2 for the liquid. So we would need a 2 in front of here to match that. So we would multiply this whole equation by 2. Now when we do this, we also have to double delta H. So I'll put a 2 in front of here, a 2 in front of here, and then this gets doubled to 88.0 kilojoules. Oh, incidentally, the delta H from the top is also given to us. We would need this number. So delta H for this process is actually negative 571.6 again. Right, so now if you take a look, the reactions should cancel out. Everything should cancel out, leaving us with this final equation. Notice that my two liquid waters, cancel out, and I am left with two hydrogens, that's what we need on the left, an oxygen, that's what we need on the left, and two gaseous water, that's what we need on the right. We've done it right, and if everything matches up, we can simply add these numbers together, so 88 plus negative 571.6, we should get a final value of negative 483.6 kilojoules per mole. And that is the answer. So a quick review, here we used products minus reactants to get the delta H. Here we use Hess's law to get the H. Be able to use both of these methods to get the delta H of a reaction. Not bad? So this is actually chapter 5. Chapter 5, remember, only dealt with the heat component of thermodynamics, only with enthalpy. Then chapter 19 adds entropy as well as delta G. So, in this case, if you take a look, we're given a bunch of entropy values for another equation. For another equation, we're given a bunch of entropy values, delta S, not delta S, but absolute entropy values. We'll get the delta S for the reaction. These also are found in the back of the book. The reaction, notice, if you take a look, we're beginning with a compound and we're breaking it down to two simpler compounds. Now, here, you can probably predict the change in S. Here we're increasing disorder because we're forming more molecules. So delta S should be positive. We're increasing disorder. Incidentally, delta H, if you were to predict delta H should be positive as well because we're breaking bonds. Well, we'll see. We'll see. We're breaking bonds, we're making bonds actually. Looks like we're breaking this bond right here, but we're making these bonds right here. So that'll we'll take a look at that a little later. So let's not predict delta H just yet. They'll ask us to do this a little later. So we have this guy, this substance on the left, placed in an insulated container where it decomposes. This is ethene and ammonia. A says, using the data in the table above, calculate the value of delta S for the reaction. So we're going to do products minus reactants, as we've done for delta H upstairs. Our two products are these. So we've got ourselves 219.3, and we got ourselves 192.8. These are our products, minus our reactants. Our reactants is this big guy, 284.9. If we do this calculation, we should end up with 127.2 joules per mole. Now notice, previously it was kilojoules, here it's joules. Entropy values are quite a bit less than enthalpy values. So delta H was kilojoules, delta S is joules. Notice our prediction is borne out because we said we're increasing in disorder, and that should work. And now they're asking us to use the data in this table to find delta H's. Now, there's a third way of finding delta H's, and that's to calculate all the broken bonds, calculate all the formed bonds, and add them together. Here, we're given the energy for each type of bond. Let's quickly do this, and I'll have to pull it down a little bit. It may get a bit crowded. Well, let me do this so I can have a little bit of space. There it is. Okay, we'll get ourselves a little bit of space for this problem. So take a look then. Let's calculate the bonds that will be broken. Now I'm going to assume that all the bonds are broken on the left side, all the bonds are formed on the right. You could keep track of specific ones because some of them won't be broken. In other words, this CH bond won't be broken. But I like to do everything that's broken and then reform everything to keep the math a little, or to make sure I don't lose anything. So my broken, I'm going to break 1, 2, 3, 4, 5 CH bonds. A CH bond is 413. So we'll do CH bonds. I got 5 of them times 413. This will give me 2065. I went ahead and did the calculation, so this is a little quicker. Then I want to break a CC bond, a carbon-carbon single bond. That's going to be 348. There's only one of them, so 348. Then I'm going to break a CN bond right here. The CN bond is 293, which gives me 293. And I will be breaking 2 NH bonds. Each NH bond is 391. So we'll do 2 times 391. This gives us a total of 782. Right, now I can total how much heat it'll take to break. Remember, anytime you break a bond, heat must be absorbed. So totaling all these up should give you 3488 kilojoules. This is how much heat, this would be a positive number, how much heat it takes to break bonds. Now, if we form bonds, let's see how much energy it takes to form some bonds. I'm going to form 1, 2, 3, 4 CH bonds. So my CH bonds, we'll do 4 multiplied by the 413, giving us 1652. We're going to form a C double bond, C carbon-carbon double bond, 614. This would be 614. There's only one of them, so 614. We're going to form 1, 2, 3 NH bonds. Each NH bond, again, is 391. There's 3 of them, so 391. We got a total here of 1173. If we total these up, now all these, I should say, these are negative because anytime you form a bond, heat is released. So these are negative values. The total is negative 3439. And then you can go ahead and add these numbers up. So we got 3488 minus 3439. This should give us positive 49 kilojoules per mole. Excellent. So it takes 49 kilojoules to actually make this work. Now notice we are breaking bonds overall, so overall we have to put energy in. But you have to keep account of all the individual broken, all the individual formed bonds to get this. So this is the third way of determining delta H. Now there is delta G. If we were asked, we're not asked to do delta G, but if we were asked to do delta G, we could do a few things. Remember that delta G is actually connected through the equation delta H minus T delta S. So you may have to use this equation if they were to ask you for delta G. Just make sure delta H again is in kilojoules, delta S again is in joules. You take your absolute temperature and combine it all, and you can actually get the delta G. This gives you the spontaneous, whether the reaction is spontaneous or not, whether it'll go on its own. Now in our case, delta H worked against nature because it was positive. Nature likes to release heat. Delta S worked for nature. It was positive. So in our case, it'll probably work as long as this term can overpower this term. So remember, this is not too far away, so hopefully you remember this. I guess we can mention this last part, C. It says, based on your answer in part B, predict whether the temperature of the contents of the insulated container will increase, decrease, remain the same as the reaction proceeds. Remember, we put this into an insulated container, and we did labs like this, where you took a thermometer in there, and if the thermometer goes down, then it's endothermic, and that's what will happen. In fact, because we calculated our delta H to be positive 49 kilojoules, we're absorbing 49 kilojoules, so the temperature of the insulated container will go down. So decrease because, now write this out for the AP exam, decrease because delta H is endothermic. Or you can say delta H is positive, indicating an endothermic reaction. Indicating an endothermic reaction. So there it is. Try some of the other problems. I'm only going to do this one, but you should be able to do most of the rest, and we'll take questions in class.